So now let me start. Okay, you are recording this meeting. Good. Now, so we continue on with hydrocarbon release. Let me see. So in the petroleum industry, hydrocarbon release is a typical kind of incident, and it can happen in the form of a gas release or a liquid release, and it can also be mist release. And the release can either be a slow release, which is what we call an atmospheric release. It releases in atmospheric condition. Or it can also be a pressurized release, which is something that's a bit more dangerous. This is when you have a difference in pressure, when you have high pressure vessel releasing it's normally a huge amount of hydrocarbon because of the pressure. And between gas release and liquid release, gas release is considered to be more significant because we know that combustion always happens in the vapor phase. So therefore it is flammable and is readily ignitable. Whereas if you have a liquid release, is normally slower and is controllable. And there are many different causes of all this hydrocarbon release, but most of it is because of material. So it's because of the equipment wear and tear. It's because that it's aging due to corrosion, or it's probably because of erosion if you have sand in the system. So these are metallurgical defects. Sometimes you use the wrong material to construct the equipment, or it can also be human errors, like you forgot to tighten a screw. Okay, so this picture here illustrates an example of a hydrocarbon release. This is an Atlantic LNG plant in 2017, and because of this hydrocarbon release, you see this mist here. Then an explosion happened after that, and three of its staffs were injured, or 3 people were injured. So there are a number of factors that determine the release rate and the initial geometry of the hydrocarbon gas release, and the most significant is whether it is released under pressure or it's released at atmospheric condition. Okay. If it's released at atmospheric condition, that if it's a gas, it will either rise or fall to the floor or to the ground, depending on its vapor density. And then not just that, it will also be directed in the path of the prevailing wind. For atmospheric release, normally when you have atmospheric release, if you ignite it, it will burn relatively close to the source point, because this is when you have enough gas vapor and it's at a good concentration with air, good mix with air, it becomes flammable. But once it's dispersed away from the source point, it becomes diluted, and therefore the flammability of that gas mixture is no longer there. So, but in the case of pressurized gas, it will release a gas jet. So you have this a stream of gas jet, and it depends on the nature of the failure. It can be directed in any direction. It can be upwards, downwards, sideways. And in this case, the release of this hydrocarbon gas or vapor will generally produce a vapor cloud. So like in the previous picture before, we have this vapor cloud. So that cloud, if it's not ignited, then fine, it will eventually just disperse away in the atmosphere. But once there's an ignition point, it will explode. Okay. So initially, so most of the time, the escaping gas is so rich, it is above the UFL. It's above its upper flammable flammable limit. So it's not flammable because it's so rich. But as wind starts to disperse it, as it's dispersed further, then it drops below the upper flammability limit and goes into that flammability zone. So that is when it becomes flammable. Okay, because you have all this wind, the turbulence that mixes the air with the gas, making it a flammable mixture. Okay, and if it has not reached or it has not met any ignition point, it will eventually just disperse and go below LFL. If you're lucky, it will just go below LFL and no explosion will occur. So the reason why sometimes explosion occur is things that are unpredictable, such as static electricity, where your clothing is just flammable and it rubs with something, causes static friction, or just short circuit in the systems. A lot of things that can cause the combustion if it's in the flammable limit. Okay, and mist or spray, it generally behaves like a gas or vapor release, but it's highly atomized and it's mixed with air. And this is easily ignited even below the flash point temperature of the material involved, because mixing of the fuel and the air has already been occurred. So spray or mist is already a mix of air with the hydrocarbon gas. So therefore it's already flammable. Now, for liquid release, it can be characterized by either being contained, allowed, or allowed to run off or spread. And if that liquid, a lot of liquid hydrocarbon is volatile. They are highly volatile. It will have dissipation by vaporization. So it will vaporize. And that vapor on top of the liquid can become is a flammable mixture. So depending on the viscosity of that liquid, it will form this pool of liquid. The higher the viscosity of that liquid, then the longer it will take to spread around. So it's easier to control. But most liquid fires are relatively easy to contain and suppress, while gas fires are prone to explosion. So liquid is always, like for example, you have oil spill in the ocean. It's easier to manage than having a gas leak. Okay, so when you have all these hydrocarbon releases, if it doesn't have any ignition point, then you're fine. You can just let nature let it disperse and dilute itself. But what's dangerous is when there's an ignition source. And you can see in this table, the ignition sources of major fires, the top of the list is actually from electrical. So there is not really somebody just putting a spark, because you know they don't have any sparks in a chemical plant. So it's most of the time from the wiring of the motors, you have 20% of the initial source of major fire is from electrical sources. And next, unfortunately and surprisingly, is from smoking. So we can see here that people do smoke around their workplace. And then third is again is caused by mechanical, which is friction. For example, you have bearings or broken parts, causing it to have a high friction and produces sparks. And it can also be a good high percentage is overheated materials or abnormally high temperatures. Sometimes you have vessels or furnaces that has a high temperature, and that can cause explosion. Okay, so these are overheated materials, hard surfaces. Okay, and then after this, these are typical ones. Okay, it's the burn of flames, combustion sparks, spontaneous ignition. These are very obvious, obvious ignition sources. All right. Now let's move on to fires, specifically hydrocarbon fires. So there are actually many different types of, several different types of fires. If you look at these three pictures, they're actually different. Okay? So there's a pool fire. Pool fire looks like this, where you have a fire that's contained in a pool, which is easily controllable, but most of the time, normally it lasts quite a long time. And then you have jet fire. Jet fires occurs very quickly, but as long as there's still source of that fuel, it will keep on firing. So this is a jet fire where it's like its name, jet. It moves like a jet. And then finally, the flash fire. Flash fire is a massive amount of fire that happens in just less than 3 seconds, I think, or less than 1 second. No, can't be. But very quick. Okay, flash fires are massive but very quick. Now let's look at the different types of fires one by one. So first of all, jet fire. So jet fire is when you have significant momentum from a source under pressure. For example, you have a vessel with a flammable liquid of gas, and then if it's suddenly being released from a pressurized vessel or a tank or a pipe that's I don't know, due to puncture or just faulty connections, then if it is ignited, then it will immediately have that kind of jet-like fire. The pressure release generates a long flame. So like you saw in the previous picture, the flame is long, and it's a stable kind of flame under most conditions. It's just that you have that long flame. It doesn't really spread around. It's just a long flame. And the duration of the jet fire is determined by the release rate and the capacity of the source. So how long that fire will sustain depends on how much release there is. If there's still hydrocarbon, it will keep on burning. Once the hydrocarbon is finished, then it stops burning, and also the flow rate and pressure. So the flame length increases directly with flow rate. Let's see, here's a video that shows a jet fire. Why you open this one? Okay. All right, so watch this. This is a chemical plant or a refinery, I think. So just a normal day of work day. There's people walking around, truck going in, accident free, I guess, for quite a while, and that happened. Actually, if you realize, moments before that happened, you can already see how he's lying on the floor. Okay, here there's explosion already happening. You see the smoke, and suddenly you have a jet fire. So that's a jet fire. See those people running. See, it's jet. It's moving like a jet because there's probably a high pressure gas being released here. So that's why you see this very fast movement of the fire. You see that it's moving outwards. So this is a jet fire. So you run. So people around here can still run away because it's pretty controllable. I would say it's just contained around this area. Okay, and that is jet fire. If I go back just now, you can see it. Okay, this one, right? Okay, wait. Okay, this normal day, right? You can see that movement. You see that? It's like a gas release behind there. There. So you can see the gas release happening before it ignites. Okay. This one is already, there's already a fire, so people are already running, so they know it's coming. Okay. Oh, come on, run! This one's running, and he is. So this guy can still walk around because I guess they know how to control it, or okay. So that is the video. Oh gosh. All right. Next type of fire is called a pool fire. It is the combustion of a flammable vapor that evaporates from a layer of liquid at the base of the fire. So this is when you have a liquid hydrocarbon release, and that liquid hydrocarbon is volatile and causes a vapor to vaporize on top of the liquid and produces a flammable fluid, flammable vapor. If it's ignited, then you have a fire on top of that pool of liquid. So that's a pool fire. So it occurs on ignition of an accumulation of liquid as a pool on the ground or on water or other liquid. So it can be on the surface of water, it can be on the ground. And normally, if you have storage tank fires, it's normally treated as a pool fire because it's contained inside a tank. A steadily burning fire is rapidly achieved as the vapor to sustain the fire is provided by the evaporation of the liquid by heat from flames upon release. A steadily burning fire is rapidly achieved. So you can achieve a steady burning fire as the vapor to sustain the fire is provided by the evaporation of the liquid by heat from the flame. So when you have the liquid, right, and you have an ignition source and there's a fire on top of that pool of liquid. So that fire can sustain long because because of the heat, the fire is hot. So that heat will continue make the pool of liquid heated. So once it's heated, while it's hot, so we keep on evaporating even at a faster rate because of the heat. So it keeps on evaporating, so therefore it provides the fuel for the fire to keep on burning. Okay, so as I mentioned, pool fire it's easier to control. It's less dangerous to human life as compared to flash fire. We will see later what flash fire is. Pool fire, even though it sustains a long time, but it's controllable, so it's not so dangerous to human life. But flash fire, another type of fire that we'll see later, it occurs in a flash. It's a few seconds only, but that is dangerous. Okay. However, the longer duration that result in a pool fire can cause greater structural and equipment damage. So the problem with pool fire is it's not really dangerous to human. You have time to run or put it out, but because that it stays long, it damages the equipment, okay, or buildings. Okay. Let's see here. I have an animation of a jet fire and a pool fire. This is just an animation. It's a medium-large release and ignition in less than 15 seconds. The jet fire and the sea fire is actually on fire escalating to area in the smoke impairment. This is on a platform. Simulation of a jet fire and pool fire on a platform. This one? Okay. So there you have a jet fire that jets out from probably somewhere like a punctured hole from a pressurized vessel, and down below is a pool fire, probably because there is oil spill. So it's liquid hydrocarbon oil spill on the surface of the water, and then it's being ignited, and you have the pool fire at the bottom of the platform. Now, flash fire is the one that happens really quick. This is a combustion event with little or no overpressure at all. So this happens in atmospheric condition, and it happens very fast, just like its name, flash. And then it's because if you have a release of hydrocarbon gas, for example, it will just immediately burn and consume the whole gas in a split second. As fuel gas is released into air, typically its concentration is very high near the release point, and it's not well mixed with the air, so the gas ignites at that time. Generally, it results in a flash fire because it happens quickly. The fuel gas has no time to spread out or disperse to greater space. And flash fire consumes escaping fuel, so it is not available for further mixing in air. So it immediately uses up all of the released gas. So therefore, it doesn't have time to be dispersed in the air. Let's see here. There's one video here that shows a flash fire. Why do you keep on going here? There's a flash fire, and it's done. Only so that was 4 seconds. So what happened is this is a simulation. So that was a simulation, and whoops, let me slow it down to slow-mo. So you have this mist of hydrocarbon. It's very flammable. It already has a good mix of air and hydrocarbon. It's released. I know well, this is simulation, but it can happen. And then this is an ignition point as a simulation. Once this mist, let's move it first. So once that mist moves and meets this ignition point, it immediately created a flash fire, and it's done. It's gone. That's all. So really fast. I think at 6 seconds. No, at 6 seconds it's gone. There's no more. It happened at 4 seconds just now. 5 seconds, it was already gone. 5 seconds gone. 4 seconds already gone. There. Just 4 seconds, and it's done. Because it has consumed all of that mist that was released on near the ground of this area. Okay. Okay, effects of fire on people. So we've seen all of the different types of fires. I think they put it in the basket. What's this? Okay, so fire. What is the effect on people? There are so many different types of fires, and do they cause death, or do you just get burned from that fire? So all these things is predictable. You can actually calculate what is the probability or the percentage of the type of injury that you can get from the different types of fire. Because fire, as you know, it has the different intensity or different strength and even length of time. Some is fast, some takes quite a longer time, some is small, and some fires are big. So all these different fires will have different effects on us, on people. Okay. So the main hazards actually that presents from the large fire is actually due to the heat radiation. It's not really that fire. That's why you know, like when you if you touch fire, right? Have you touched fire before? You don't really get burned, right? Kan? Have you touched fire before?
No, yes.
Right.
Okay.
So if you touch fire, you don't really get burned. But it's the heat from the fire that burns you. If you have like a fireplace, if you go really close to it, your skin can get burned from the heat of that fire. It's not really from that fire. Okay. And also it depends on the duration of time that you're exposed to that fire. You know, when you touch fire, you do it only in a second, right? You just touch it for a while and then you don't feel anything. It's only a split second. But can you just touch the fire and leave it there for maybe longer than 1 second, 5 seconds, 10 seconds? No, right? And then it starts burning. Oh, I think it's starting to burn my finger. Okay. So the length of time is also a factor of the extent of injury that you will get. Okay. All right. So a first degree burn. What is a first degree burn? So have you ever maybe accidentally touched something hot, like a pot, and then your finger becomes red, or your hand becomes red because you or maybe you know telangga your motorbike, right? There are parts of the motorbike that's hot, and then your legs suddenly it becomes red. So that's a first degree burn. So first degree burn only affects the epidermis, which is the topmost surface of your skin, and it causes a mild level reddening of your skin, but it's reversible and erythema, and then you don't have any blisters. Okay. Because it's only the epidermis layer is affected, and it's probably happened really quick, so you don't have that blisters forming. Okay, and it normally goes back to normal around 24 hours. Now, have you ever touched something hot and then after that you have blisters forming? Anyone ever experienced that? You have blisters after you have touched something hot. Do you know what blisters are? You know what blisters are? Yes. What are blisters? You don't know what blisters is?
Don't know.
You know that kembung-kembung and then you have the liquid inside?
Pernah. Yang kembung tu.
Yes. I don't know what it's called, but blisters lah. So and then there's like water inside it and you poke it, there's liquid coming out. Have you ever had those?
Pernah.
Okay.
Yes.
Blisters. If you have blisters, for example, like these, it means that that is a second degree burn. So second degree burn is characterized by the formation of blisters, and the size or the size of that blisters, whether it's shallow or whether it's a huge blister, depends on the what do you call? Depends on how severe the burn is, because even for second degree burn, there are many degrees of second degree burn. There are many like grades. Yeah? And the second degree burn normally this is when the burn affects also the dermis area, not just the epidermis. So it affects the dermis layer, and then the surface layer of the skin is damaged. So you have a further reddening of the skin. So in more severe cases, the whole of the dermis is damaged. So the dermis is a thick part of the skin. So the more severe the case, then it goes further deeper in the skin. Now, what about if you've seen burn victims who are totally black? If you got burned and then the whole skin is black, so that is a 3rd-degree burn. If the whole skin is black, it means that the burn has gone down to the subcutaneous layer of the skin. So the epidermis is totally burned, is black, and then the dermis is also damaged, as well as the subcutaneous layer. It's and then, so how do you get to these different types of degrees of burns? What is it? I don't know, over there. Just use the probe. Okay. So again, it's the length of time that the person is exposed to the thermal radiation, and that length of time depends on the person itself. Depends on how fast you are to react to the fire. Okay. The longer the duration, even at low thermal radiation, can produce serious physiological effects. And what is that factor that determines the duration that you are exposed to fire? One of it is that person's ability to run, for example, or the person's age or strength, or if the person is disabled, the person is not able to run. So those are factors that extends the length of time that the person is exposed to fire. All right, so this diagram shows how the difference between the 1st-degree burn, 2nd-degree burn, and 3rd-degree burn. So 1st-degree burn or superficial burn is only when you have this reddening or the erythema. It's normally goes back to normal in 24 hours. It only affects the epidermis layer of the skin. But for partial thickness burn or the 2nd-degree burn, it can go down to the dermis area. Depending on the severity, it can go further down. This normally causes the formation of blisters, and you have those the circular liquid filled blisters. A full thickness burn or 3rd-degree burn will cause you to have that black skin, blackened skin, and it affects even down the subcutaneous layer, and sometimes even affects the muscle of the person's body. Well, but most of the time, once these are all burned or injured, then you start to have infection. So that infection is the consequences of this burn if it's not treated correctly, and then that infection can cause the muscle to get affected. So now, you can also die, okay, from fire. For 3rd-degree burn, there's actually a high chance that if it's depending on which part of the body is being burned, it can cause fatality. So burn or death is direct consequence of the intensity of the radiated heat flux from the fire and the exposure time. So this is two major factors. One is how intense is the fire. Second is how long you're exposed to it. And to determine the number of burns of death, so normally we use the thermal radiation dose. The thermal radiation dose is like the dosage of thermal radiation that you have received. So the thermal radiation dose is depicted by this capital D. It's in watt/second meters. Is equals to the time. See, it's equals to the time, the effective time that a person's exposed to that heat flux, times the amount of heat, the heat flux, which is more in watt per meter square. So you can see it's the time times the amount of heat, and that is the thermal radiation dose. So this thermal radiation dose value can be used to determine the severity of the effect of that fire. Okay. Okay, so the exposure time, that T just now, depends on the human factors most of the time, and also the type of fire. For example, if we're talking about flash fire just now, for flash fire, it only occurs in a few seconds only. Okay, so the time there is short. And then there's also, but let's say if you are in a pool fire can sustain long. Okay, and if that person just stands there and not doing anything or not running away, then the time of exposure to the fire is longer. I know, like somehow he's just disabled, not able to run. You know, I'm not sure. Okay, and then another factor that affects the exposure time is the position of that person in relation to the fire. So if, I don't know, was he lying down or was he sitting down when the fire occurred? As compared to, well, he was standing up, so he has he's more ready to run away from the fire. So it's the position of that person, whether he's near to it or far away from it. And also the time it takes to react and how he reacts when he realizes the event. Does he run fast, or is he a slow runner? Can he sprint? And then the person's age too. Is if he's an elderly person, that person might not be able to run as fast. Or a physical condition, is that person not fit to run, or just somebody who's disabled, who needs wheelchair. So those are things that affects the time that that person can run away from the fire. Okay, so and then I mentioned just now, in the case of fireballs or flash fire, it's equal to the duration of the fire. It's normally less than a minute or a few seconds for flash fires. In the case of pool fire and jet fire, the duration of the fire is longer because you have that the source of hydrocarbon is always there. So the person's exposure time to that heat flux depend on how he reacts to that fire and then run away. Okay, so that exposure time just now, the T, is usually taken as equal to the sum of the initial reaction time plus the time is required to reach the safe point. So let's say this is where the fire is and you're standing here. So the time starts from time 0 when the fire starts until this person run away until he reaches a safe place. So that's the total time, which is the exposure time. Okay, so the exposure time is TR plus X0 minus R divided by U, which is TR is the reaction time. Normally this is taken as 5 seconds for you to think and react. And then X0 is the distance between the flame and the position where the intensity of the heat flux is lower than 1 kilowatt per meter square. So 1 kilowatt per meter square is that safe heat flux radiation that a person can receive. And then, yeah, T effective is that exposure of the person to that heat flux. And R is the distance of the person from the surface of the flame, and this is in meters. And U is the velocity, the escape velocity, normally 4 meters per second, that a person will sprint to escape the fire. But that's really okay. That's quite okay. All right. Now, so how do we predict the probability of a certain type of fire to injure somebody or to cause death? So this can be done using a simple calculation. And what we need to estimate the probability of the effects from fires, we normally use a dose-response curve. So a dose-response relations have been created from experiments, from field data, and for a lot of different parameters such as thermal radiation, overpressure, heat, noise, concentration of toxic gases, and etc. And right now, the most widely used method is called the Probit function. So this Probit functions can be used for many different types of accidents to predict the probability of death or injury. But in our case now, we will use this Probit equations for the effects of fire. So we look at fire first. So the Probit equation is Y equals to K1 plus K2 natural log V. So this Y is the Probit variable that we need to look, and that will give you, that will tell you what is the intensity or the effect of that fire. And then K1 and K2 are constants that you can look at tables from Probit tables. And natural log V is the causative variable. In our case, because we're looking at fire, so V is actually the thermal radiation dose, which is the D that we saw just now, the D, thermal radiation dose, which is the effective temperature times the heat flux. Okay, so the amount of radiation that you get, the dosage of radiation that you get, okay, which is the temperature times the heat flux. So that's our D, which is the V. Now K1 and K2, these are calculated values or already published values that you can use. For example, if you want to know what is the percentage of first degree burn, so this would be the K1 and K2 value. If you want to calculate how much second degree burn, then you use this K1 and K2. If you want to know how many people would die from that accident, and then you use that value K1 and K2. Okay, so, and then once you calculate it, once you put in K1 value, you put in K2 value, and you know what is the thermal radiation dose, you can get Y. And that Y is a value between 1 to 10. Okay, so Y is a value between 1 to 10. And then from that, you can use this table to find out what is the what is that value in percentage. So let's try one example. You can take out your calculators, pencils and pens and papers. Okay, so let's find out what is the percentage of people that will suffer first degree burn, second degree burn, and death if that person is exposed to a thermal radiation dose of 9 million watt second meter. Okay, so this is your D. Okay, let's say you have this amount of thermal radiation dose. So you want to know, is it going to cause people to have first degree burn, second degree burn, or death? So we want to calculate these three. How many people would die? How many people would get severe burn? How many would get just a superficial first degree burn? So we use the Probit equation. Y equals to K1 plus K2 natural log V. All right, so a good way to do this, let's put it in a table. No, not put it in table. We go back to that table just now. The values for K1 and K2, and the thermal radiation dose here for our calculation is 9 million, right? Okay. For first degree burn, the equation becomes Y equals to negative 39.83 plus 3.0186 natural log D, natural log 9 million, and then you calculate. For second degree burn, Y equals to negative 43.14 plus 3.0186 natural log D, and then you do for death. So death, you put in the Probit equation, it's minus 36.38 plus 2.56 natural log D. So try and then calculate what is the value for Y for all these three cases, because we want to know how many will die, how many will actually get second degree burn or first degree burn. Anyone? Calculators?
Tengah calculate.
Okay. Then, so first degree burn, what is the Y?
8.51.
So first degree burn,
8.51.
8.51. Okay. Second degree burn,
5.196. 196. Tak tahu betul tak?
5.19,
196.
5.2 lah.
Yes.
Right. And death,
4.6.
4.6. 4.6.
Yeah.
Yeah. All right. Okay, so we have all these values. So let's look at what it means. But basically, you can see that first degree burn is a high value. Second degree burn is a lower value, and death is a low value. So it actually already indicates that there's a high chance you get first degree burn, a high chance that you get, and then a medium chance that you get a second degree burn, and then quite some percentage that you get people will die from this burn. But to accurately to get a more accurate percentage, so we go to this table, which is we transform the Y value from Probit. So these are Probit value. So to transform Probit value into percentage. No, so let's see. Put this away. First of all, Y equals to 8.51. If you look inside here, do we have 8.51? So you can see the numbers. Actually, these are 2, 3, 4, 5, 6, 7. So the numbers actually increases, right? Where's 8.51?
Tak ada.
Tak ada. So the highest number is 8.09. Alright, so let's just say we take this, okay, 8.09 lah. So that means that if you read 8.09, it actually says 99%. So that means that more than 99% of people will get first degree burn. Okay. And then for 5.2, do we have 5.2?
Yes.
Mana? Ni Kan? Okay, so that's 5.2. So if you read here, you go here, it actually says that it's 50%, and you go up. So this means that this is 50%, 58%. Second degree burn is 58%, and death is 4.61, which is here. 4.61 is 30.
35.
35. 35. So this means that okay, so actually for 8.51 it's actually 99.9 kan. This is actually above 99.9, so close to 100%. So almost everybody will get first degree burn if he is exposed to 9 million watt meter second of thermal radiation dose. Almost everybody will get first degree burn. And then 58% of the people, there's 58 chance that they will get second degree burn. That is more than 50%, right? More than half of them will get second degree burn. They will start to have blisters, and then death is about 35%. Okay, so about 30%, 35% of the people will die, okay? Or a chance they will have a chance, the chances to be fatal, to have some fatal cases for 9 million watt meter second of thermal radiation dose. Okay. All right. So that is our results just now. So you can actually say that for first degree burn, 100% of people will be affected. Okay. And then second degree burn is 58% and death is 35%. So that is how you use the Probit equation for the effect of fire on people. Any questions?
Ada.
So we have the slide. So let's look back at what we have covered. We have covered fire triangle. Fire triangle tells you that to start a fire, you need 3 elements. You need to have what? You need to have a fuel.
Ignition.
You need to have an ignition source, and you need to have an
Oxidizing agent.
oxidizer, yeah, oxidizing agent. And then we looked at fire explosions, flammability, the flash point, fire point, ignition point, and then UFL, LFL, all these terms. And then we looked at the flammability diagram. So we drew the airline, the stoichiometric line, and so on. And we calculated LOC also. And then today you were introduced to pool fire, jet fire, flash fire, and then we did some calculation using the Probit equation to calculate the probability of the effects of fire on people. Okay, so that is the end of our slide. Discard. And we will continue on with the next topic, which is explosion. So we have covered fire. So right now we go to explosions. Would you like to take a break for a while?
Sure.
Or we can continue?